All right, ladies and gentlemen, welcome back to another video with Mr. Kenton for AP Chemistry. Sorry for getting these videos up so late, but I guess better late than never. Hopefully next unit I'll be a little bit more on top of things. But we're continuing by looking at Unit 5. We're looking through kinetics, and we're going to talk about reaction mechanisms. And specifically, we're just going to introduce kind of this thought process of what a mechanism does and how we can use it to help us understanding rate laws, right? So without really spending too much time, let's just dive right into it, right? So as we've seen in this unit, we've come to realize that when it comes to chemical reactions, it's not as simple as just a one-step process. Sometimes that might be the case, but we start to see from our mechanisms that we've been looking at that reactions typically take place in multiple steps, though we're typically just interested in the initial and final processes. Kinetics allows us to look at what's going on in between, right? And so let's consider the following reaction. We've got nitrogen dioxide plus carbon monoxide reacts to produce nitrogen monoxide and carbon dioxide, right? And so it seems like a pretty straightforward process. And let's say that you're given the following mechanism. You're told this is how this reaction occurs, right? This is how we go from reactants to products. And so with the first step, there's two nitrogen dioxide molecules that react to form a nitrogen trioxide and a nitrogen monoxide, and it gets designated as the slow step. All right, kind of remember that's your rate determining step, right? And then there's a second step where nitrogen trioxide reacts with carbon monoxide to produce nitrogen dioxide and carbon dioxide, and that's designated as a fast step. Right? Now, one thing to recognize or that you should be able to observe about your mechanisms, that when you add them together, you should be able to add up and make the overall reaction that you're trying to make. Now, I'm going to go ahead and make this designation. We can look at this, right? We can see that this is going to simplify, right? We can notice that, let's see here, an NO2 is going to get canceled. NO2 is going to get canceled, and an NO3 is going to get canceled, right? And if you add those together, you're left with NO2 plus CO produces NO and CO2. Now, I wanted to go ahead and cross those out just because I know that a little bit later there's going to be some black slashes that pop up that are in the wrong spots. So we see that those add up. Now, again, so we see that we get the overall reaction. So if we have a mechanism and it doesn't add up and give us the overall reaction, it's probably not a good mechanism. Now, like we just stated, or like we just showed in this particular example, we wrote this out as two elementary steps, right? We had the slow step and the fast step. And so if a reaction proceeds via several elementary steps, then those elementary steps must add up to give our balanced chemical equation, just like I've been saying. Now, the one thing that you might have noticed as we were going through and doing this process, we ended up producing something that we didn't see in the overall process, right? And if you think about it, that would have been the NO3, right? NO3 is nowhere to be found in the reactants and products of our overall reaction. And so NO3 is going to be what's classified as an intermediate, right? It's a species which appears in an elementary step, which is neither a reactant or a product. And what's going to happen is your intermediate, it's going to be formed in one elementary step, and then it gets consumed in another, right? So in our case, it was formed in the first step, and then it was immediately consumed in the second step. So nitrogen trioxide was our example of an intermediate in this particular case. Now, let's take a look at another example. Let's think about the decomposition of ozone into oxygen. So we're provided with the following mechanism. They don't tell us whether it's slow or fast step. Typically they do. So you've got ozone goes to oxygen and free radical oxygen. And then you've got ozone plus that free radical oxygen producing two oxygen atoms. Right? Now when you add everything together, you end up with two ozones are going to produce three oxygen gases, right? And that's just by simply adding together the two elementary steps that were provided. And then our intermediate in this case is that free radical oxygen, that oxygen that isn't bonded to itself. Okay, pretty straightforward, I think. And the only other thing I want us to consider before I kind of close out this particular video is you can have mechanisms that have a catalyst in it, right? And so remember just what a catalyst is it's something that's able to speed up the rate of the reaction in a given chemical process. So it has been proposed, it has been noted, like with ozone, for example, that in the presence of free radical chlorine, so chlorine that's just by itself, it's not diatomic chlorine, that reaction can be sped up. And so what we see is that the catalyst will appear in the rate determining step, but then it will appear as a product in a later step. Overall, the catalyst, just like the intermediate, does not appear in the overall reaction. And so if you look at the following mechanism that's been listed here, you have Cl plus O3 goes to O2 and ClO, and then you have O plus ClO goes to Cl and O2. So for our overall reaction, we get O plus O3 makes 2O2. And what we should notice about this particular process is that the difference between the intermediate and the catalyst is the catalyst shows up as a reactant and then it's consumed as a product, right? So in this case, that free radical chlorine, that's our catalyst. So Cl is the catalyst, right? And then we see that the chlorine monoxide that we have here, which I'm just going to kind of circle in red, that's going to be our intermediate in this particular mechanism, right? But again, we still see that when we look at this, we still end up with the same net result. We still get ozone that's being converted into oxygen, right? And this just so happens that that chlorine catalyst, this reaction might be faster, and so it might occur more often because it's following a faster reaction rate. All right. Now that's a very brief introduction to reaction mechanisms. Hopefully that makes sense. If you do have any questions, please don't hesitate to ask. You can certainly come to office hours. You can fill out the Google form and type in your question there, and I'll be more than happy to get to the questions that you guys have. Thank you guys for joining me. Look forward to seeing you guys again soon. Take care.